Hello, this is a video on how to perform COMSOL simulations for microfluidics. This is specifically for BYU's TEMP Lab. So we're going to be taking a 3D model from openSCAD, showing you how to import it into COMSOL, and then showing you how to perform finite element analysis in COMSOL on that 3D model. So the first thing that you'll need is your openSCAD model. In this case, we have a super simple microfluidic device. The red section here is where fluid A goes into the chip. The blue section is where fluid B goes into the chip. And they converge in this purple channel and mix in that purple channel. This yellow channel right here is the heating channel. It just has liquid gallons in it, and there'll be a current running through that, which will cause it to heat up. And then this transparent bit that you see right here, that is all PEG-DA. Okay, so now that we have that, in your openSCAD model, make sure that you have a display component selection. It's super important that we can isolate each component of the model to be able to import each separate bit into COMSOL separately, rather than importing it all as one. So now that we have that, I'll show you the process of importing each of those elements into COMSOL. I already did this beforehand, but I'll show you one of them just to make the process a little bit easier. So we'll focus on our fluid channels, the red, the blue, and the purple here. So to do that, I'll call my channels display component, which will show just my channels, and then simply all we have to do is hit save. That'll save the document, and then we have to open a software called freeCAD. FreeCAD's really cool because it has an openSCAD interface, so you can import openSCAD files and export them as step files, which openSCAD doesn't have the ability to do. So what we'll want to do is go to freeCAD and then create a new document and then open your file that you saved before in openSCAD. This will import, in our case, the fluid geometry, which is just what we need. Then after that, you're going to want to select group over here. That'll make sure that the entire fluid channel is highlighted. You can just double check to make sure everything's there. Sometimes when you open stuff in freeCAD, everything might not be selected, so you just have to go through this tree and find where that bit that's missing is and enable it, and then select it as well. But once you have that group selected, go to File, then Export, and then you want to make sure to save the file type as a step with colors. That is super important because that's the type of file that COMSOL can read. And then just save it as whatever you want to save it. And then just hit OK. And then it's now ready to be imported into COMSOL. So just make sure you go through and do that with each of your components in your openSCAD model. And when I say each of your components, make sure it's like each thing that has its own physics associated with it. So in this case, for this simple chip that I showed you, we have our channels, which I just showed, our heater, which would be just that, and then our chip body. So we'd want to export all of those three things separately, open them in freeCAD, export them as steps with colors, and then they'll be ready for COMSOL. Okay, so now we're going to go over COMSOL and how to set up the simulation. So you'll open up COMSOL and it'll look kind of like this. So the first thing you want to do is you want to go to Model Wizard. This is just an easy way that will set up the basic things for your simulation for you. Then we'll be doing a 3D simulation. And if we go back to our chip, just so that we can see it, let's think about the physics that are involved in this simulation. Okay, so, well, we have, obviously, a channel that's going to be heated up. So we're going to want to use heat transfer in solids and fluids for that. And then we're also going to have fluid that's flowing through that chip. So we'll want to include laminar flow. And the laminar flow that you're going to want to use is this laminar flow right here, the blue and the orange. There's a second laminar flow that's just blue, this one, and we actually don't want to use that one. The really nice thing about this blue and orange laminar flow is that it's a multiphysics module. So it'll link your heat transfer in solids and fluids to your laminar flow rather than having them be isolated. So make sure to select this one. Double click on it. It'll automatically add this heat transfer in fluids. We can delete that because we have our heat transfer in solids and fluids already. The next bit of physics that we're going to want to add is joule heating. This is essentially our Gallenson having the electric current sent through it and heating up. So make sure to add that. This will automatically add heat transfer in solids. We can delete that again because we already have heat transfer in solids and fluids. So we're good there. And then the next thing that we're going to want to add is transport of diluted species. So this is essentially mixing two fluids together. There's also a transport of concentrated species. They're pretty similar. It honestly just depends on the problem that you're using, whether or not you use diluted or concentrated species. For this tutorial, I'm going to show you how to use diluted species. Okay, and that should be all of the physics that we need. So now that we've added all of the physics that we need, we can hit done. Sometimes it takes a little bit to load. Just have to be patient with COMSOL. Okay, so when it loads, you'll get thrown into a screen like this, and you might not have these bars on the side either. It might look something like this. So the first thing that we're going to want to do is import all of our geometry from those files that we exported in freeCAD. So to do that, we just go here to geometry, right click, and you click import. And we're going to have to do this for each separate piece. So the first thing that we're going to want to do is import the body. So let me just go find that real quick. Okay, so here's our body. So we just want to import that, and that'll import it. Okay, the next thing we're going to want to do is import our channels. There we go, those are imported. And then the next thing we're going to want to do is import our heater. Okay, so here's what we have now. Now this is a little bit hard to see because it's not transparent. To turn transparency on, you just click this button right up here, and now it's all transparent. So we can see what's going on inside. Okay. Sometimes when you import things into COMSOL, this one imported very nicely, but sometimes when you import files into COMSOL, they don't import in the correct locations on the chip. To import things to the correct location, all you have to do is go to Geometry, then Transforms, then Move, and then you select what you're going to want to transform. Let's say I wanted to transform this, and then you just throw in the distances that it'll be transformed. In this case, it's fine. Don't have to transport anything. So we're good. Okay, so our geometry is looking pretty good. The next thing that we need to do is set up our materials. So we'll want to think about what all of our materials are in our chip right now. In our case, we're going to want to add materials from library. And we're going to want to add PegDA, because that is our chip body. We're going to want to add Gallenson, because that is our heating channel. We're going to want to add stainless steel because those are our needles. We're also going to want to add water, just because that's the fluids we're going to use just for ease of simulation. And then we'll also need to add air as the surrounding material for the entire chip. And we'll use this built-in air right here. Okay. Another thing that I forgot to add, going back to the geometry, is adding the air around our chip. So, to do that, we'll just go to geometry, and we'll add a block, and we'll just make the block pretty big. We'll do 30 millimeters in all directions. Cool. So it has that now. And now we'll want to center this cube around our chip here. And I'll just roughly do that. In our case, that is -15 plus 3 millimeters. This won't be exact, but it'll be close enough. I recommend centering exactly when you're performing an actual simulation on your chip. Oh, this is actually -2.5. 15 plus 2.5. Okay. There we go. Roughly centered. Great. Okay, now going back to our materials, we need to assign a material to each piece of the chip. So we'll start with a PEGDA. Luckily, the first thing that you choose is automatically assigned to everything, so we don't need to adjust anything in here, because when we reassign our materials, it'll override what we've already assigned. So we'll move on to Galveston next, and for our Galveston, we just want our heater channels. So to do that, we're going to want to hide everything except those heater channels, just so we have easy access to them. So you're going to want to click on this click and hide button up here, and it'll hide the components that you click, which is great. And now we can click that again to deselect click and hide, and choose our Galveston channel. There we go, that material's been assigned. And now we can reset our hides, and everything's back. Great. So now we're on our stainless steel. We'll select that. Right there. Now our water, which is just this right here. And now we have our air. There we go. Okay, that's all of our materials selected. Now, don't be worried when you see these X's on the materials. Right now, because we haven't set up our other physics, it's trying to apply a few values to these materials that we don't actually need. So these X's should go away when we finish setting up our physics. Okay, so we'll step into heat transfer in solids and fluids. This one's relatively easy to set up, which is great. So just open this drop-down menu and you'll see these 4 values. So the first thing we're going to want to do is define what our fluids are. By default, everything is defined as a solid. So we're going to need to define our fluids. In our case, that would be the air, and then the water, and we could define our Galveston as a fluid because it is a liquid metal. However, defining the Galveston as a fluid rather than a solid doesn't affect the simulation too much, it doesn't affect the results of the simulation too much, but it does greatly increase the time that it takes to compute. So it's generally a better idea to model it as a solid. Okay, the next things that we're going to add to heat transfer in solids and fluids are reference temperatures. So right click on heat transfer in solids and fluids and then add a temperature. So this is going to be everything that's at room temperature, or whatever temperature we define in our simulation. In our case, that is going to be the cube of air. That's going to be at room temperature. So just select all faces of those. And then we'll also model our needles as a constant temperature because they stay roughly the same, even though they do heat up ever so slightly. So make sure to just select those needles too. And then, there we go. That's everything that's at a constant temperature. Now that should be everything for heat transfer in solids and fluids, which is fantastic. Next, we'll want to set up our laminar flow. Now this one's a bit more complicated. So, the important thing about laminar flow is making sure to only select your fluids that you're focusing on. In our case, we're not super worried about the flow of the air. We don't really care how that's flowing. So we'll deselect everything. That's what this does. And we're really only concerned with the flow of the water. So we'll just select laminar flow for our water here. There we go. Okay, now that we've selected what is going to have laminar flow, we're going to want to make sure to check include gravity and use reduced pressure because this is a microfluidic device. We're also going to want to make sure to change the compressibility to incompressible flow. Now that we've done that, we can step through fluid properties, just check to make sure that it has Newtonian and for material, we're good there. If you want to have an initial pressure, you can set that. In our case, we're not going to worry about this. And then you can go through your walls, just make sure the walls are correct on your fluid channels. Make sure it also has no slip as the wall condition. And then under gravity, make sure negative G const is defined in the Z direction. Okay. Next, right-click on laminar flow, and we're going to want to add an inlet, or in our case, 2 inlets, and an outlet. So make sure to add all of those. Okay, we'll go to our first inlet here, and we'll have the first inlet be that left cylinder right there. And we'll say it has an inflow velocity of 3 millimeters per second. And then we'll just do the same thing for inlet 2, 3 millimeters per second. And we'll define where our output is, which in our case is right there. Great. Now that should be everything for our laminar flow. Next, we'll step into our electric currents. Okay. This one's relatively simple as well. In our case, we're going to only want to select the things that have electric currents running through them. That'll be our Galveston and our stainless steel. Nothing else will have electric currents running through them. So we'll clear everything and select just our Galveston and our stainless steel. And then we can just check all of these just to make sure they're good. The material type, we'll generally want to just select for a material. That's usually easiest. Electric insulation is usually fine. And in our case, because we're using Galveston, we're going to be sending a current through it, so we don't have to worry about the initial voltage. Instead, we're going to want to add a terminal and a ground, and then select one of these needles as our terminal. And we'll say, I don't know, 0.1 amps of current running through it. This is something that you can set yourself. You can choose whatever it is. And then for our ground, we'll select the faces of this needle as our ground. and that's electric currents all set up. I'll come back to transport of diluted species because this is probably the most complicated one. So for now, we'll step into our multiphysics. So we're looking at our non-isothermal flow for now. So the first thing that we're going to want to do in non-isothermal flow is to make sure that our heat transfer in solids and fluids is selected for our heat transfer module, and our laminar flow is selected for our fluid flow module. Under material properties, we're going to want to make sure to check this approximation, otherwise it will not simulate correctly. This approximation will only appear after you've selected include gravity in laminar flow. So make sure to set up laminar flow before you set up the non-isothermal flow multiphysics module. And that should be it for that multiphysics module. Next, step into your electromagnetic heating. Just double check to make sure these modules are selected correctly, electric currents, and heat transfer in solids and fluids. Now that's everything for your multiphysics. Okay, we're going to go back to transport of diluted species now. The very first thing that we're going to want to do in transport of diluted species is to check how many different fluids are mixing. In our case, we're going to be mixing 2 different samples of water. They're going to be the exact same thing, but COMSOL will be able to show them as 2 different fluids mixing. So to do that, we're going to want to go to our dependent variables and change the number of species to 2. And then rename this one to C1. So now we have our 2 fluids, C1 and C2. Now that we've defined that, we need to go back to our geometry, and we need to split that mixing channel into 2 separate channels. So to do that, we need to add a work plane. Since we're splitting, let me show you which channel we're splitting. We're splitting this channel right here in half. So to do that, we're going to add a work plane, and that looks like it's the YZ plane. And now we need to find the x-coordinate of that channel right there. Now that can be a little tricky, especially considering a lot of things in openSCAD are written in pixels and layers. So the best way to do that, I've found, is to go to your openSCAD model and simply write an echo statement that'll tell you where your channel is located. In our case, I know that this channel is located halfway across the width of the chip. So I wrote this echo statement right here, which will just tell me the dimensions of the chip. Okay, it looks like it's 7.6 millimeters. And the width of the chip is 7.6 millimeters, so we'll go back to COMSOL, and we'll say that this work plane is 7.6 divided by 2 millimeters. Okay, then we can check build selected just to make sure that's in the right spot. That looks like it's in the right spot to me, right down the center of the channel. Great. And then what we need to do is we need to go to Booleans and partitions and select partition objects. So the object that we're going to partition is our fluid channels, and we're going to want to partition it with our work plane that we just made, and select that work plane, and then we can hit build selected, and as you can see, that split our channel in half. Perfect, just what we wanted. Now we'll go back to our materials just to double check that they're all fine still. Oh, sometimes it does ask for a gas constant just in case your water were to evaporate or something. In that case, our gas constant of water is 461.52. Okay. Sorry, we're going to want to go back here and just double check to make sure everything is still selected correctly, even with our partition. So we'll just take a look at this. Okay. Checking our water. and it looks like it is still selected correctly. We'll go into Laminar Flow just to double check our inlets and our outlets are still selected correctly. It looks like they are. Perfect. Okay, now we can go back to transport of diluted species, and we can define everything that we need to with our two species. So you can define your diffusion coefficients here. I'm just going to leave them as default. This is largely material dependent. Then we can go to our initial values. This is one that's pretty important. So these are the two concentrations that we have. Our one concentration of water and our second concentration of water. I'll set both of these to about 1 for now. Again, this is just a random value I chose, but this is one that's important to set in your problem. The next thing that we're going to want to do is we're going to want to add an inflow. Well, I guess 2 inflows since we have two inputs, and an outflow. Okay, so in our inflows, we're going to want to select where that input is. In that case, that's that face right there, and that face right there. Okay, so for inflow 1, we're going to want to define the concentration of each fluid. We'll say each of these inflows has a complete concentration of one of the samples of water. So we'll just say this is 1 mole per meter cubed of that one, and 1 mole per meter cubed of that one. Great. And now we'll just select our outflow, which is right here. If it'll let me. Oh, we forgot to select sorry, going back, we forgot to select what is what transported diluted species is being applied to. So we'll do that real quick, clear it all, and select all of our domains that have it. Right there and right there. Okay, cool. Now we can go through and select our outflow right there. Okay, cool. Now that should be everything for transport of diluted species set up. Okay, so now that we have all of our physics set up, we can define a mesh. So just a brief description of a little bit on how COMSOL works. What it does is it splits your geometry into tons of little polygons, and it solves tons of equations for each of those polygons, and the mesh defines how those polygons are divided up. The finer of a mesh you use, the more polygons it's going to make. So it's going to take a lot longer to run the simulation, but it's going to be a lot more accurate. If you use a coarser mesh, it's going to use less polygons, but be a whole lot less accurate, but it'll compute really fast, which is great. So I suggest usually starting with a coarser mesh, and as you refine your simulation and your model, you can work your way up to a finer mesh. Do note, though, that some physics, if there's too coarse of a mesh, will not converge on a solution, particularly laminar flow. Sometimes if you use too coarse of a mesh, it doesn't converge. So I'm going to choose an extra coarse mesh. And that'll just create a mesh for my model. Great. Sometimes it throws warnings that edges are shorter than your minimum element size. Don't worry about that. It'll simply just go to the next size up for you automatically on those regions where it's too short or too narrow. Okay. So now that we've made our mesh, we need to add a study. To do that, go to the Study tab up here and hit Add Study, and go to the time-dependent study. Okay. Let me explain a little bit between the difference of time-dependent studies and stationary studies. So stationary studies look for an asymptote that the simulation will converge to. It can be useful sometimes, but most of the time time-dependent studies are better, or more useful, as they'll show values at a specified time. Okay, so now that you've added the time-dependent study, you can go to it and you can select the time range and the step size that it'll compute. I'll just do 0 to 10 seconds with a step size of 0.1. Great. And then you can select here what physics it's going to solve for. In our case, we want to solve for all of those, which is great. And then we can hit compute, and this will start running all of the calculations on this model that we set up. Oh, it looks like we forgot something. We forgot the electrical conductivity of our Galveston. Let me go back and add that real quick. When you add your Galveston, you just have to define what your electrical conductivity is. In our case, that is 3.46 times 10 to the 6th. Okay, there we go. Now our study should be good to go. Okay. As you can see, it is computing down here. Now, while your study is computing, there are two very important plots that show up. Your convergence plot 1 and your convergence plot 2. Convergence plot 1 is particularly important. You want to make sure that all of your variables here are converging with an error below at least 1. If your lines are staying well above 1 for a long time, that means it's not able to converge on a solution, and it could potentially try to compute for a really long time. So if it stays above 1, just cancel your simulation. But if it's staying low for a while like this, in our case 10 to the negative 2 and lower, this is looking pretty good. It looks like it is going to converge on a solution, which is great. Sometimes it can take a few minutes for COMSOL to converge on a solution if your geometry is simple enough and if your physics are simple enough. And sometimes it can take multiple hours. It all depends on how complex your geometry is, so just be patient and understand that it can take a while sometimes. Okay, it looks like our simulation is just about done, which is great, and it generated a whole lot of plots for us, which is great. It looks like the ones that we have here are temperature, isothermal contours, velocity, pressure, electric potential. Oh, it looks like it was not able to completely compute electric potential, so we'll have to go back and edit that later. But it looks like it was able to compute everything else, which is fantastic. Right now, all of these are at time equals 0, so if we want to look at any of these at a different time, we just change our time to, let's say, 10 seconds, and then you hit plot, and you can see it changed. Now, these auto-generated plots can sometimes be useful, but honestly, this doesn't tell us much, just looking at these colors. We want better figures. So to do that, we'll start by getting a 2D color map of the heat along our fluid channel, because that's something we're interested in. And then we'll get a line graph of the heat along our channel as well, particularly in the mixing section, because that's really what we care about. Okay, so to do that, we're going to want to go to our data sets, right-click on it, and then in our case, we're going to want to add a cut plane. That'll create a 2D data set that we can work with, which is significantly better. Okay, so in our case, we want to figure out the z-coordinate. Oh, we'll want to put this on the xy plane, and we'll want to figure out the z-coordinate of our channel right in the center. Again, we'll want to go to our echo statement in our openSCAD model and figure out the channel location in the z direction. In our case, that's at 2.5 millimeters. Okay, so we'll go to COMSOL and throw in 2.5 millimeters, and then you can hit plot just to double check that's in the right spot. Looks like that is. Great. Okay, cool. We have that data set now. And now that we have that data set, we can go to results here and add a 2D plot group. And we'll want to select that cut plane one that we just made and hit plot. As you can see, now that created a little plot right here with that plane that we selected. Just what we wanted. Now we need to assign what variable this plot is going to show. So to do that, we're going to want to add a plot type. And in our case, we'll add a surface plot, just so that we can see a color map of the heating of the channels. This is where we define what variable we're solving for. If we were solving for velocity, we'd do V for example. If we were solving for our concentrate, we would do C1 or C2. But in our case, we're doing temperature, so we can just leave it as T. Keep our units in Kelvin, and then hit plot. And as you can see, it has shown the heating of our chip. Because I define my current as so low, the temperature variation is pretty small, but this does show the temperature of the channels at 10 seconds. Fantastic. You can zoom in on these plots to look at exact locations. You can zoom out. You can do whatever you want with them, which is great. You can take a screenshot of them to export them somewhere, and you can obviously change the time, and it'll change the data. There's 9.6 seconds. If we go back to about 1 second, you can see it's different. Okay. Now that we've got that, we want to work on getting a line graph of our temperature along this mixing channel, because that will be a whole lot more useful than this color map right here, because we can't really obtain a lot of data from this. So to do that, we're going to want to add another data set again. And we are going to want to add a cut line 3D. We'll add a cut line 2D. That's usually easier. We'll reference our cut plane 1 in this case. And now we want to know exactly where this channel starts and ends. And we'll just add a line right through it. Again, this is where the echo statement is crucial. I know that this channel right here starts halfway along my chip in the x direction and halfway along the chip in the y direction. So it'll be 7.6 divided by 2 for both the x and the y. 7.6 divided by 2, and then make sure to set it in millimeters and not meters. And then this chip, or this line, will end at 7.6 millimeters in the y direction. And just to double check that we got this right, we can hit plot. And yep, that looks right. This red line right here is our data set. Great, so now we have our cut line 2D. Now to get a line graph from this, we're just going to want to go to results and then add a 1D plot group. It creates this blank plot for us, which is great. And then we'll want to add a line graph. And we'll want to change our data set to our cut line 2D. So it'll reference that one line that we had. And we'll want to keep our expression as temperature. Yep. And then we can hit plot. And this will create a line graph for us, which looks kind of crazy right now because it plotted every single time from 0 to 10 seconds. That's not really what we want. So to fix that, we just go back to our 1D plot group and change our time selection to manual, and we can add a time index in, or we can go to interpolated and select a time. If it's a value that's between one of our steps, it'll interpolate. If it's on one of our steps, it won't interpolate, and it'll just display that step. I suggest sticking with your time values that are on one of those steps that you chose. In our case, I know that 10 is one of those steps. So we can change that to 10 seconds, and now this will display the, oh sorry, you need to select it in this one too. 10 seconds. This will display our line graph of that temperature across the line that we defined in our cut line 2D right here, this line from here to here at 10 seconds, which is great. So we can see that right where the fluids mix, the temperature of that channel is quite a bit higher, and right by the exit, the temperature of that channel is quite a bit lower. That's useful data. Super, super useful, because we can adjust our channel geometry to flatten that out a little bit more if we want to, which is fantastic. Another thing that can be useful, rather than having to generate like 50 million different plots of this, like, I don't know, let's say I wanted to look at 5 as well to see how it's changing over time. I could go through and select each of these, but honestly that's kind of a pain. Something that's super useful is adding an animation. I'll show you how to set up an animation in the player, which is just locally in COMSOL. But if you want to get a GIF of this animation, just select File and follow the same process. So I'll add an animation in. One second, it takes a second for it to load. Okay, there we go. Now that we have our animation, we can select our 1D plot group 11, which is where we made that line graph, and it'll animate that line graph for us. It'll show how it changes over time, which is very, very useful. As you can see, it's roughly the same. And let's say we wanted to do this with our color map too. We could also change that to our color map, and we could see how that changes over time as well, which is super useful. It's almost there. Okay, there we go. As you can see, that's how it changes over time. And I'd suggest going through these settings, adjusting them, playing with them, figure out what works for you with all of these, because they're very useful. And again, just step through all of these, look at all of these different plots that it generated for you, make your own plots, do whatever you need for your data set, and experiment with these plots as well. There's a whole ton I could go into with how to visualize and collect your data from COMSOL, but I'll just leave you off with these simple line plots with temperature, because honestly these are the most basic and most common things that you'll want to obtain from COMSOL. Now, that's about it that I have for today for how to set up a microfluidic COMSOL simulation. Yeah, good luck with your simulation.